Thank you. Okay, so I'm going to start with an apology. It's never a good way to start a talk, but at least it's honest. In 2 hours, I'm obviously not going to be able to give you a complete understanding of what Lattice QCD is and what you can do with it. So it's going to inevitably be unsatisfactory, but hopefully I'll give you at least an indication of what the ingredients of this approach are. And there are some quite good textbooks you can go and read if you're interested and want to follow up. So yeah, I'm going to talk about Lattice QCD and some of its applications. And broadly, what I want to address over the 2 hours are what it is as a tool, what you can do with it, and what you can't do with it. So I understand you've already had some lectures on what QCD is, so I probably don't need to linger too much on defining the theory, but I'll just remind you of some things so that we're talking about the same quantities. So quantum chromodynamics is a quantum field theory in which the relevant fields are quark fields, fermions, and gluon fields, which are vector gauge fields. And the important defining characteristic is this threefold symmetry group. The theory is defined by its Lagrangian. Here it is. And it's a complicated looking thing. It features this gauge covariant derivative where you see the gauge field the gluon field is sitting there between the quark fields. And there's this bit that is just a function of the gluon field. And the important thing to realize is the properties of these fields. So you have quark fields, they're fermions, so they have a Dirac spin index and they have a color index running 1 to 3. And then there are the gluon fields, which are these 3x3 traceless matrices that can be expanded in terms of the generators of SU3. So this is all the mathematical structure of this. I think you saw this already in some earlier lectures. But let's just think about what the content is, what the basic ingredients are of a theory like this. Well, the first bit is this first term can be split up into two pieces. One, which is the Dirac equation. So this is describing the motion of relativistic spin half particles and antiparticles of mass m. And you know that often with quantum field theories like this, you choose to represent the properties of the theory in terms of Feynman diagrams. So there you go, there's the propagator for a fermion. The other part of this first term gives rise to this coupling between the quark field and the gluon field in terms of the color vector current. So this is how quarks produce gluons and vice versa. And then in the third term, you have the piece of this expansion that has 2 powers of A, and that gives rise to the propagator describing a massless gluon. So here's a gluon propagator and they're massless. And then the bit that makes QCD really interesting is when you expand this out, you have pieces which have 3 powers of A and 4 powers of A, and that gives rise to these gluon self-interactions, which importantly are controlled by a coupling strength, which is exactly the same coupling strength that appears in the quark-gluon coupling. So there's just this one dimensionless coupling G that appears in the theory. So that's what QCD is. The problem, of course, is that at lower, it's known that the coupling constant is not a constant. It runs with energy, it runs with the scale at which processes you're interested in are happening. And importantly, at low energy scales of below a few GeV, it takes large values. So the usual way that we approach quantum field theories in terms of perturbation theory is simply not going to work. And that's also apparent not just from the theoretical side, but from looking at experimental observables. So if you look in experiment, of course, we don't see quarks and gluons, we see hadrons. So clearly, quarks and gluons are bound into hadrons. Binding is a non-perturbative effect. Perturbation theory at a finite order will never bind a system. There are other slightly less obvious aspects. The QCD Lagrangian, when you write it down, has quark masses in it. And everything we know about those quark masses is that they're extremely small. For the up and down quark mass, they're extremely small. which would say you have an approximate chiral symmetry in your Lagrangian. But if you look at the spectrum of hadrons, there is no sign that there is a chiral symmetry in the theory. Chiral symmetry would say for example, for every negative parity baryon, there will be a degenerate positive parity baryon. That simply isn't true experimentally. So the expected chiral symmetry is not present. In order for that chiral symmetry to get broken, you need non-perturbative physics. In perturbation theory, every diagram will be chirally symmetric. So it's got to be something non-perturbative. The fact that quarks and gluons are confined, not just bound, but confined, you can never see them, this must also be non-perturbative in origin, and we could make a list that's very, very long here. So clearly we need a non-perturbative calculational tool within QCD, and ideally one that's first principles. So by first principles here, I mean proceeding without making a priori unjustified approximations or assumptions. Yes?
Binding is beyond perturbation theory. Is it just the binding between quarks and gluons or any other sort of binding?
No, that's true in any quantum system. If you have you can basically think about it in the following way. In order to have binding, you have to have a pole in a propagator, right? And a pole in a propagator is like 1 over p squared minus m squared, for example. Now expand that and that has to be a function of the binding strength of the interaction strength G. If you expand in a power series in G to any finite order, you can never get something of the form 1 over p squared minus m squared, right? You'll just always get a polynomial. That's a non-polynomial behavior. So you can never have binding in any perturbative theory. You have to resum sense to get that to happen. So yeah, so we want a non-perturbative calculational tool that's first principles, and Lattice QCD offers this. So I'll be very careful with words here. It's a non-perturbative approach to QCD. It is approximate for reasons you'll see in a second, but it is systematically improvable. That means the approximations we're about to make are ones that can be improved upon by changing something in a systematic way. So how do I explain this? So in order to explain what Lattice QCD is, it's important to start thinking about quantum theories in one particular way, and that's in terms of the path integral approach. So the path integral, you might be familiar in ordinary quantum mechanics. So it's a good idea to do this by analogy. So let's think about non-relativistic quantum mechanics in one space dimension and consider the simplest possible thing, a free particle, which is moving between some definite initial position to some definite final position. Then you know that classically, not in a quantum theory, but classically, there is one and only one path that particle will definitely follow. You know exactly where it is and exactly how fast it's going at every point. You obtain that path by solving Newton's equations, but equivalently, it is also the path that has the least value of action. If you take the Lagrangian and evaluate it for this particular path rather than any other path, you will get the lowest value of action for that path, right? This is the principle of least action, which is essentially equivalent to solving Newton's equations. So that's fine. That's what classical mechanics is in one statement. But quantum mechanics does not behave like that. Quantum mechanics, in order to get the right results, you look at a quantity like this amplitude, which is the amplitude to go from xi to xf, from ti to tf. Okay, this is like a propagator. And it has this representation, and all this means is you don't just consider the classical path, the path of least action, you consider every possible path that the particle could take between these 2 points, and you add them up. So this is a fancy sum. You add them up in a particular way where you weight each one by a phase, which is given by the action. And if you've taken an appropriate quantum mechanics class, you will know that from this start point, all of conventional quantum mechanics arises. This is a completely equivalent way of thinking about quantum mechanics as the Schrödinger equation. So you get exactly the same physics out of it. But it turns out to be a very convenient way to formulate for the following reason. So now let me go to a quantum field theory. So before jumping into this with loads of mathematics, let me just draw an analogy. So this is to classical physics as follows. Classical physics was one particular path obtained by solving the equations of motion, Newton's equations, which is the path of minimum action. Quantum mechanics is some overall paths, weighted by this factor. Simple. So what would this be going to the analogy of a field theory? Well, first of all, what is a classical field theory? Well, a classical field theory is something like Maxwell's electromagnetism. Right? You know this. You have Maxwell's equations. If you give me a set of charges and currents distributed across space, I can solve Maxwell's equations and I will get a unique field configuration of electric and magnetic fields, right? Which you can plot. Fine. Well, Maxwell's equations there are doing the same job that Newton's laws did in classical mechanics. There are equations of motion. You give them some boundary conditions, which are the charges and currents, and you solve them for the fields. So the fields are doing the job of the path. That's the analogy. It may not be obvious to you, depending how you were taught electromagnetism, but there is an action for a field configuration. Such a thing can be defined, and lo and behold, the solution of Maxwell's equations is exactly the field configuration that has the lowest value of action. So from this, you can probably guess what a quantum field theory is. A quantum field theory is, don't just take the classical field configuration, but take every possible field configuration, compute the action for that field configuration, and sum over all the field configurations. So there you go. That's a whole semester of quantum field theory in 2 minutes. That's basically what it is. So let's make it slightly more concrete. Let's think about something simpler than electromagnetism. Let's think about a scalar field theory. So a scalar field is something which is, a real scalar field is something which is a number at every point in space and time. That's a real scalar field, as opposed to, say, a 4-vector. Which electromagnetism would be. So here's a Lagrangian for a real scalar field theory, and the details don't matter, except to say this bit deals with the kinetic energy and mass, and any interactions you want, you stick in this potential-like thing over here. But classically, this is a simple object. Say it again. It's just a real number at every point in space and time. That's all it is. Just like the electric field is a vector at every point in space and time. So as I just said, the way to make this into a quantum field theory is to sum over all field configurations. So a configuration is just all the possible values that this can take at every point in space and time. Pick one, that's one configuration. Pick another, that's another configuration. Obviously, they're an infinite number. And weight by this factor where the action is just the integral of the Lagrangian density. Is that a question? Oh, someone outside, sorry. Okay, this quantity here called the path integral might be a bit cryptic. It's not clear what obtaining the value of this is actually going to tell you, and the answer is actually tells you nothing. But you can express things that are interesting, like correlation functions. So this is an example of a correlation function. This is the vacuum state. These are the fields now interpreted as operators, because this is a quantum theory. And you see it's very closely related to this representation. You just have these extra fields sitting under your weird path integration. What is a correlation function? Well, probably the simplest analogy, the one that you might want to think about, is a classical example would be the spin vectors in a ferromagnet. So, you know, in a ferromagnet, you have a crystal of spins, and you know that if you apply an external field, they'll all line up. But if instead of applying it because of the mutual attractive interactions that tend to line them up, if instead of doing that, you just had a disordered set of spin vectors, and then you picked one and lined it up in a particular direction, you might want to examine what the spin vectors at various distances away from it do in response to that lining up. That's what a correlation function is. And obviously by studying the distance away from that point, which is the distance between these points, you learn something about the interactions. That's why correlation functions are interesting. So clearly you can compute these the following way. Of course, the problem is, you know, I can come along and write this scripty D thing here, but it apparently means nothing other than saying sum overall configurations. Well, you sit down and think, how on earth am I going to sum overall configurations? And obviously, that's not easy to do. So if we go to just one dimension, you see, look, here I've drawn 4 configurations, but there's an infinite number of them. So it's not the case that we're going to parameterize all of these, and I mean, it's just not obvious what to do. It's not obvious whether that integral is really defined. But in fact, the way that you derive that integral tells you how to deal with it. And the way to deal with it is to discretize the space. It's to not consider the space to be continuous, but split it up into equally spaced slices. And then the correct, true behavior should come as you make that slice separation tend to 0 as a limit. The reason this helps is now, if you think about the sum overall fields here, now it's going to be a product of the value of the field at each space-time point. So I've tried to illustrate this here. Here are my 4 different configurations. Here's one slice, and you see each configuration has a different value at that slice. So you imagine if I keep drawing more and more configurations on here, I'm just going to densely fill up all the possible values here. And at least in a hand-waving way, you can see if I integrate over all values, that's going to at least include all possible configurations here. Proving that that is a rigorous statement is a bit more effort, but it is true. And of course, you do this for each slice. You integrate over the value of the field from -infinity to +infinity at every space point. Or in general, in a 3+1 dimensional theory, at every space-time point. So that's the idea. So usually if you're dealing with, say, a quantum field theory in 3 space dimensions, 1 time dimension, you'll use a hypercubic grid, so a 4-dimensional square cubic grid. So that you introduce a lattice spacing, a single spacing between points in space and time. Now, then at each point, you want to do this integral over the value of the field from -infinity to +infinity. So this is just what you saw on the previous slide, boosted up into however many dimensions we're interested in. But of course, a rather obvious problem is, if we try to study the entire space-time, then there's an infinite number of these integrals, because there's an infinite number of points. So that's kind of problematic. So we also put in the whole system into a finite space-time volume. So we only go out so far in space and time. And we have to stick some boundary conditions on this. I'll gloss over that for the moment. But what you realize is if we do this, then a field configuration now is a finite number of numbers, because there are only a finite number of points on our space-time grid now. So a field configuration is just a list of numbers that terminates because you run out of points. And whenever anyone says to you list of numbers, you should immediately think computer, because computers are fantastic at doing operations on lists of numbers. We're terrible at it, right? We get bored after about 3. Computer never gets bored. So this is pushing you in the direction that this is going to become a computational problem. And indeed, that's true. The problem is you're still dealing with these integrals here. It's a finite number of integrals, but still, it's a large number of integrals. And so what that says to you is, well, maybe don't do that. Instead, maybe do what's called a Monte Carlo approach to doing these integrals. So rather than trying to do each integral exactly, do the following instead. Just randomly generate field configurations, right? Field configuration is just a list of real numbers. Computer will happily randomly generate lists of real numbers. And then for each one, evaluate the action, which is just do some operations on those numbers to spit out a real number. And then do the sum here just as an average, just average over very large numbers of randomly generated configurations. So, right, so what we want to do is randomly generate these configuration values, compute the phase, and average over them. And the idea of Monte Carlo integration is if you do enough samples, you will approximately capture this value. Problem is it works really, really badly here because a phase is a terrible thing, right? This is a number of magnitude 1 just moving around the complex plane. So you can imagine that the problem here is you get massive cancellations. If you get if you think about the unit circle, you get a phase here and a phase here, they exactly cancel each other. So you just get extremely sensitive cancellations in this. And you need enormous numbers of configurations to get something accurate. So this doesn't work in practice. This is what's known in numerical parlance as a sign problem. They're very, very bad. They're not solvable, basically. So we do something, and we do something which makes people's stomachs turn, but is correct. We take the time variable and we say, well, let's make it imaginary. Stop it being a real value and let's make it an imaginary value. Okay, so let's just proceed as though that's a reasonable thing to do and not the action of a mad person. Then this quantity minus I times the action, which was the space-time integral of the Lagrangian density, that extra factor of I changes this from being a phase, from being imaginary to being real. And then that means this phase here becomes essentially a decaying exponential. And this is very nice because this is now a bounded real number. What's more, it's pretty clear that low values of the action are going to have largest contribution, which is sort of what classical physics indicates to you, right? In the classical limit, the minimum value of action should be the only one present. So this sort of looks reasonable. And the fact that it can now be interpreted as being like a probability. This is a weighted sum, weighted by probabilities. So if it is justified to do this, this looks very promising for a Monte Carlo approach. Now, I won't go into the details here. You can ask me about this or you can read it later. In fact, this is completely justified. And in fact, it's more than completely justified. Anyone who tries to sell you a quantum field theory and doesn't do something like this is lying to you. Quantum field theories don't converge unless you do something like this. The integrals you encounter, they're just not convergent. And you don't describe real physics. But I don't have a lot of time to linger on that. You can ask me if you really care. So once we've got this, then actually this sets us on our way, because we can now interpret this quantity as being the probability for a particular field configuration. And this indicates now an efficient way to do this. Rather than just completely randomly generating field configurations, instead, if you can generate them according to this probability distribution, then you will do what's called importance sampled Monte Carlo, which is to say that those field configurations that have the largest value of this probability will appear more often than the field configurations which have small value of this probability, but by definition of drawing them from this probability distribution. So you will sample the most important fields more often. And that's basically what is done in lattice field theory. You obtain an ensemble of configurations, some finite number of configurations, according to this probability distribution. Now, how you do that in practice, how you write a numerical algorithm that draws from this probability, okay, that's where the magic is, right? That's hard. That's a numerical computational problem. But we don't need to worry about that because we just care about the physics output. But the thing I want to emphasize is configuration sounds cryptic. I'm going to say it yet again. It is just a number at every point on the grid. So as far as your computer's concerned, this is an incredibly simple object. It's a text file with a list of numbers, a list of real numbers, and it couldn't be simpler. So what do you do if you can generate a bunch of these configurations and store them to disk? Well, as I said, this quantity, the path integral, what I've even forgotten what it's called. What do we call it? Yeah, it's just called the path integral, isn't it? That's right. Doesn't matter because it's not of any interest. It's basically one. It's basically a way to measure one. What you need is correlation functions. So here's an example, right? So you always take vacuum, so the empty state matrix element of some function of the fields. So previously you saw a 2-point correlation function, right? The value of a field here, how does it correlate with the value of a field here? So roughly speaking, if you wiggle the field over here, what does the field over here do? That's what a correlation function tells you. So it's easy to compute a correlation function now, right? This is the path integral definition of that correlation function. But if you have drawn fields from this probability distribution, then all you need to do is average the value of this operator acting on the fields over your configurations. Right? If you draw from a probability distribution and just average over the things you have drawn from, you will get the correct answer. That's what drawing from the right probability does for you. This is just the definition of an average. This is not any more deep than it looks. It's just the definition of a weighted average. The nice thing is you get an estimate from this, not just of the mean value of this correlation function, but you also get an estimate of the uncertainty because, of course, you've only used a finite number here, and you should have used an infinite number. So how important is that? Well, that's self-diagnosing because you compute the variance. Compute the variance on each of these from each of these configurations, and you know how averages work, right? The more samples you have, your mean gets closer and closer to the correct answer, and your variance gets smaller and smaller, unless there's something perverse about your probability distribution, and you get a better and better estimate. So this is nice. So this is one way in which lattice field theories are systematically improvable, kind of a trivial way. If you just want more and more accuracy, more and more precision, I should say, well, accuracy is also true. You just do more and more configurations, and you just keep going until you reach a level of uncertainty that is tolerable to you. But that's kind of trivial improvement, systematic improvement. Okay. But QCD isn't a scalar field theory. So obviously I was showing you a scalar field theory because it's easier to think about nice, simple, real numbers at each point in space-time. We've got to go back to handle quarks and gluons, fermions and gauge fields. And here it gets a little bit more complicated, but the conceptual picture is exactly the same. So the first thing you have to realize is you've got to figure out a way to efficiently introduce the gauge field, to parameterize the gluon field in an appropriate way. And this is done in a slightly odd way, because you will think of the gluon field as being this thing A. But actually, in lattice field theory, lattice gauge field theory, we don't do that. We do something different. So let me motivate this for you in the following way. Consider the product of a fermion field and its conjugate at two different space-time points. So you see they've got a color, I'm hiding the spin, but they've got a color index hanging off them and a space-time index hanging off them. And the problem is this quantity, this product here, where I've just contracted the color indices to try and make something that looks colorless, by doing a simple contraction, this doesn't work in the sense it's not gauge invariant. So if you know what a gauge field theory is, the idea is you're allowed to do an independent gauge transformation at every point in space and time. And anything that changes its value when you do that is gauge non-invariant and generally bad, for some definition of bad. So that's not great. But the solution to this is known. You introduce something called a Wilson line. So you connect these 2 points by this sort of weird exponentiation of the value of the gauge field sort of integrated along some path between the 2 points. And if you've taken a class in this will be obvious. If you haven't, it'll look weird, but take it as read. This quantity is gauge invariant. And essentially, the reason it's gauge invariant is whatever gauge transformation you do on this quark field gets done in a compensating way to the gluon field just next to it. And the gluon field just next to that gets done in a compensating way. And you get compensation along the lines. The gauge transformation gets dragged along the line and cancels out everywhere. So this is called a Wilson line. In a sense, it transports the color from here to here in a gauge invariant way. So why am I bothering to show you this quite complicated thing? Well, the point is when you put your system on a lattice, you can't just connect these 2 points by any line you want, because you've now got this grid, and the grid is everything. There is no space and time in between grid points. So if you're going to try to do something like this, you're going to have to replace it by some kind of path that sticks to the links, so that goes between neighboring grid points. That's the only consistent way to define such a thing. And then it's immediately apparent to you, well, there's a shortest possible gauge link. There's a shortest possible Wilson line, which is from one point to a neighboring point, like that, or like that. And so for obvious reasons, we call that a link. And that's the minimal possible Wilson line. And from the fact that this was an integral, you now realize, well, this integration sort of goes away if you're just dealing with one link, and it's just replaced by the distance, which is A. So the link is this. It is just the exponentiation of the gauge field. But if you know group theory, you know that the gauge fields are proportional to the generators of the SU3 gauge group, and an exponentiation of the generators are just what are called the elements of the group. So this, written like that, is just an SU3 matrix. It's a 3x3 matrix that is unitary and has determinant 1. Yeah. Yeah, so for example, here, this would be U, this is UX in the mu direction. If you're at this point here, that same link would be U of X plus mu in the minus mu direction. No, you still only have 8 real numbers per link, because that's just at this point, there's another link here having 8 real numbers associated with it. Oh, you're thinking about the different directions. Well, that's a different link. That's a different link to this one. For each link, there's still 8 real numbers. Okay. Unless I've made a mistake, I don't think I have. It doesn't matter whether it's 8 or 16 anyway. It can be any. As long as it's a finite number, you can still do this. Okay. So that's how you're gonna store the gauge field configurations. But obviously you've got to take the QCD Lagrangian and replace it by something that only evaluates the fields on the points, the sites and links of the lattice, because that's the only thing that has any meaning. But remember, the Lagrangian has got derivatives in it. Derivatives are continuous things. So obviously you're going to have to do something like a finite difference. And indeed, that's what you do. So if you consider the following quantity, so this is the quark field evaluated on lattice sites. So here at X and X1 hop on, and there's that gauge link we just talked about. So this first term is describing fields here and here. And the second term is describing fields here and here. And we're just taking a difference, which is like a finite difference. So this is the analog of doing this in good old-fashioned calculus. Okay. And then you say, well, what is this quantity? Well, we can Taylor series expand this quantity in small a. just like you would do over here. And lo and behold, what you get out of it is something that looks like the first term of the QCD Lagrangian. So that's what you want. The idea is this is a discretization of the first term in the QCD Lagrangian. And there are many, many other ways to do this, right? Just as there are an infinite number of finite difference approximations of a derivative, there are an infinite number of ways to construct this. And some may be better than others. We're not going to worry about those details. But we can do this. You can also do it for the gluon field bit. It's tedious. It looks extremely complicated, but take it for granted you can do that. So if you do that, well, let's focus on the quark piece first. Here's the quark bit and quark gluon bit of the action. What is this going to look like after we've discretized it? Well, it's going to look like this, or something similar to this, but you realize that you can write this in the following complicated looking way. Here is the quark field at every possible space-time point, every possible color, and every possible spin. Here is the conjugate field at every possible point, every possible color, and every possible spin. And in between them is a matrix connecting the two, which is a function of the gauge fields, the links everywhere on the lattice. This clearly is the most general way to write a bilinear form like this. And this matrix gets called the Dirac matrix. It's a matrix in space-time, color, and spin. And so it's worthwhile to stop and say, okay, this is going to be a numerics problem, right? Before we start coding this up, let's figure out how much memory we're going to need. So typical lattice size in modern calculations might be 24 sites in each space direction and 128 sites in the time direction. Don't ask me right now why you want more in time. Complicated. It's not complicated, but I don't want to go off topic. So you can do that multiplication and then multiply by 3 colors and 4 spins, and you will get 21 million. So this matrix is 21 million by 21 million. You need 100 petabytes to store that matrix. If that is not apparent to you, at some point a few years ago, I looked up the complete set of all printed material in the world ever is 200 petabytes. So that's not happening, right? That's clearly not happening. But something saves us. And what saves us is this matrix is in fact incredibly sparse. Almost every element of this matrix is 0, exactly 0. And you can see why here. It's nearest neighbor. There are only non-zero elements between a given site and its nearest neighbor, and all other space-time points are 0. So in fact, this matrix needs nowhere near this amount of memory because you store it in sparse format. So sparse format is the idea that you don't store all the zeros, you just store a list of the non-zero positions and their corresponding values. And of course, that's drastically smaller, enormously smaller. So, okay, we can handle such a thing. We can construct such a Dirac matrix easily enough. So what are we going to do with it? Well, so a gauge field configuration, as we've discussed, is simple. There's a load of links on the lattice, and at each one, there's an SU3 matrix. There are 8 real numbers. Fine. Text file with a list, 8 real numbers in each row, 1 for each link. No problem. Perfectly easy. We could all code that up in 5 minutes. What about the quark fields? Well, here we hit an interesting wrinkle in the representation of fields in the path integral formalism. The famous thing about fermions is they anti-commute, right? This is what's interesting about them. And the problem with that is it means the fields anti-commute. So psi1 times psi2 is equal to minus psi2 times psi1, which ordinary numbers do not have that property. And the problem is under a path integral, everything is not an operator anymore. It's just a number. But numbers don't anti-commute, so we're in trouble. So the problem is you actually need a different kind of number to represent fermion fields in a path integral, and they're called Grassmann variables. And Grassmann variables are those objects which have this anti-commuting property, where, yes, they anti-commute with each other, and the square of any Grassmann number is 0, for obvious reasons. But this doesn't sound like the sort of thing you want to put on a computer, right? I don't know if you've tried to type a Grassmann variable into a text file before. You know, you're going to struggle to do that. Fortunately, we don't have to. So here's the cute thing. Because the QCD action is bilinear in the quark fields like this, the bit of the path integral that is the integral over the fermion fields, this looks complicated, but really this is a Gaussian, right? This is e to the minus x squared. It's just that x is a Grassmann variable instead of an ordinary variable. And you'd need to refer to a textbook to see the details here, but this integral can be done exactly. And it turns out that its value is just the determinant of this matrix. Nothing cryptic, the real determinant, the thing you learn in high school determinant, right? Just ordinary determinant of a matrix. And what's left over is just an integral over the gauge fields. And the whole action, the whole physics of the quark fields is hidden inside this determinant. The cost is the probability that we want to draw the random gauge fields, gluon fields from is not just the exponential of negative the action anymore, but it's this combined thing with the determinant of m. And that's irritating because while M is a sparse matrix, it is still quite difficult to compute the determinant, even of a big sparse matrix. So computationally, this is something that takes a lot of effort to evaluate, but it can be done. So this is what we do. So whereas before we talked about the scalar field and generating configurations according to that probability distribution, e to the minus s of phi. Just do the same thing here, but with this more complicated looking object. And this is completely defined, and this is completely defined. So if you hand me a gauge field configuration, a list of these numbers, I can write a little subroutine that will return the value of this combination. Quite a long time after you asked it, because I have to compute this thing and that will take forever, but it can be done. Okay. Then this can be turned around and this used as a probability distribution from which we draw these DUs. And then the story is the same as with the scalar field. Any quantity you're interested in, you just compute by averaging over these gauge configurations that you've computed. Yeah.
But is there any way of looking at that determinant inside of the integral as like a Jacobian?
So actually the best way to think about this physically, I mean, it sort of is, but the best way to think about this physically is think about, while waving your hand significantly, think about the gauge field here as possible vacuum states, as possible distribution of gluons in the vacuum. Now, the one thing you'll have been told about quantum field theories is they have this property that like particle-antiparticle pairs keep popping out of the vacuum and then annihilating and disappearing again. Well, where's that? Where is that physics? Physics is all in there. So actually, if you expand this in powers of the coupling constant, it will look like a sum of loop diagram of closed quark loops connected to gluons. So what this is it's all the quark-antiquark bubbles in the vacuum popping up in exactly the right weighting to be a quantum field theory. So here's something you can compute. Here is a correlation function, and this would be your guess, a first correlation function to compute. It's the correlation of the quark field at one point with the quark field at another point. And if you've studied quantum field theory, you recognize, oh, this looks an awful lot like the propagator. This is the propagator for a quark to go from one place with a color and a spin to another place with another color and a spin. And it has a path integral representation, which looks like this. So, fine. So how does this go? Well, we separate out the bit which is the gauge field, and the bit which is the integral over the quark fields, and we see, this is different. A moment ago, we didn't have this, and we did the integral exactly and got the determinant. Well, this is not much more complicated than that. This is the same story in ordinary mathematics. If you know how to evaluate a Gaussian, it's not much harder to evaluate a polynomial times a Gaussian, the integral of a polynomial times a Gaussian. So if you can do you can do the integral e to the minus x squared, I bet you can do the integral x squared e to the minus x squared. Same story, right? This is basically that. And all that happens is every time you get a quark field and its conjugate, you get one factor of the matrix inverse of the Dirac operator. If you have multiple factors, you get multiple matrix inverses. If you've taken quantum field theory, you'll start to smell something familiar. This looks like this thing called Wick's theorem, where every time you have a field and its conjugate, you connect them together with a propagator. Well, this is exactly that. This is that coming out of path integrals. So look at what we've got here. It's the sum over all the gauge fields, the inverse of the Dirac matrix on that gauge field, multiplied by this thing that we drew gauge fields from. So if we want to compute this, all we have to do is compute M inverse on each configuration U and average them. So just do this. And that will give us the value of this correlation function. This thing, for what I hope are obvious reasons, we call the quark propagator. It's essentially describing the propagation of the quark through that particular gauge field configuration. So, straightforward. Draw your gauge field configurations, compute this on each one, average them. Okay. I mean, actually don't do this, because what you will do is get 0, because this is a gauge variant quantity, and if you average over gauge fields, you'll just get 0. So don't do this. Unless you save these as you go along, because these objects are useful. It's just their average is 0. But let me show you how these objects are useful. I will stop soon. So here's a correlation function that shouldn't be 0. So I'm calling this a meson correlation function for the following reason. Look, this is a particular combination of quark fields. And this one, this gamma 5 here, this makes this whole combination be, well, this whole combination is a color singlet. The color is all contracted and the fields are at the same space-time location, so no Wilson line is needed. And the spin structure gives this combination pseudoscalar quantum. So spin 0, negative parity. If you know the rotational properties of these fields, you can prove this. And all I'm doing is correlating this operator at one particular space-time point, which I'm calling the origin, with the same operator at every other space-time point on the lattice. But I'm choosing to sum over space positions. And the reason I'm choosing to sum over space positions is that projects me into 0, 3 momentum. So you know, momentum projection is just Fourier transforming. If you choose P equals 0, the Fourier transform just becomes a sum. So that's what that is. So by doing this, I'm trying to write down something which has pseudoscalar quantum numbers and is sitting at rest. It's got 0 momentum. So I'm trying to correlate a pseudoscalar at one time with a pseudoscalar at another time, for reasons known to me. We'll see. We'll see why. So how do we do this? Well, you just do the same thing as we did a minute ago. You write down the path integral representation, you split it into a product of a bit with the gauge fields and a bit with the fermion fields. Now you've got more fermion fields, so you'll have more M inverses. And indeed, you have 2. You have 2 M inverses, one from contracting this with this, and one from contracting that with that. And so there they are. And there are these gamma 5s which act in spin space. But this looks complicated. But really, it's just a bunch of matrices multiplied together and then traced. Computer will do that for you happily. Give it a bunch of matrices, multiply them all together, sum the diagonal, no problem. And it's helpful, because this is hideous, to draw a drawing which shows what that is. It looks a bit like a Feynman diagram. So we represent the gamma 5 sitting at this space-time point by this blob, the gamma 5 sitting at this time point by this blob, and the things that appear in between are these propagators. So we draw them like propagators. So this drawing just represents that, and it looks a bit like a Feynman diagram in that it's got propagators in it. So looks good, right? Well, except I've pulled a fast one, because I've implied that this M inverse is something you can get. Well, M was sparse, right? Full-blooded M was 100 petabytes, 21 million by 21 million. The problem is that the inverse of a sparse matrix is not sparse, it's dense. So the full inverse of M is back to 100 petabytes. That's problematic, to say the least. So knowing that, I have not attempted to write something down that requires the full M. Notice I didn't go from every space-time point to every space-time point. I went from one space-time point to every space-time point. So what appears here is not the whole matrix M inverse, but just one column of it. So I only have to find one column. So that's now, roughly speaking, 21 million real numbers. Sounds like a lot, but it's not. That's a few gigabytes. That's absolutely fine. So you can compute what's called a point-to-all propagator, which is just one column or row of this thing. And I won't linger on the point here, but it's just solving a sparse linear system for a point-like source. This is just the numerics of it. This is perfectly easy to do, straightforward to do. Techniques exist to do it. So this, I'll finish the first lecture here. So this makes it clear that we can compute this correlation function. The reasonable question would be, why are you computing this correlation function? Next lecture, right? But you can do it. Let me give you the Lattice QCD workflow, because now you have the ingredients to understand this. So what are the approximations that have been done? Well, we had to discretize the theory. We put it on a space-time grid. You have to choose a particular discretization, right? You're doing finite differences for derivatives. You've got to pick a particular one. There's loads of choices here, but you have to choose one. So you choose one. When you do that, there actually are some parameters. I haven't lingered on that, but there are the quark masses, for example. And at some point, you're going to have to specify what the lattice spacing is. How do you do that? Well, it gets hidden inside some parameters that appear in your action. So you have to do some work to figure out what the parameters are so that you describe the version of QCD that you want to see. But I will make an important point here that you should address to anyone who claims they're doing calculations in QCD, some theoretical technique that is QCD. To really do first principles QCD, all you should have to supply is minimal experimental input. So if you are studying stuff at low energies, all you should have to supply are enough measured quantities that you can set the quark masses and the value of the coupling. That's it. So in the isospin limit, where up and down is treated as the same, you should be able to get away with 3 hadron masses, say the pion mass, the kaon mass, and the proton mass. If you are having to supply anything else, start asking questions, because it's not first principles anymore, because you're needing to supply more information than you strictly need. But okay, I don't want to linger on that. So you've tuned your parameters, you've discretized, you've tuned your parameters, you've now got this det m e to the minus sg as your probability distribution. Monte Carlo generate hundreds of gauge field configurations. Hundreds is the typical number you want. To do that, you need big computers. To do that for realistic lattices, you need big parallel supercomputing. And these calculations are typically done on the world's fastest computers. This is not a joke. This is really, really serious computing. But you write a proposal, you send it off to some agency that's in charge of a supercomputing facility. They get external reviews. You get rejected the first 4 or 5 times, and then you get lucky and you get the time and you generate it and you store the gauge field configurations. And in one of the great ironies, you spend enormous amounts of supercomputing time to produce these tiny files, right? Because the actual number of numbers needed to describe a gauge field configuration is really pathetically small, right? So you save those to disk. And because they cost so much to generate, you also put them on a tape, and you get that tape pulled out and put somewhere safe, because for sure you don't want to have to generate them again. But you've got them. Then you get these M inverses, right? You've got to compute these M inverses in order to compute anything interesting. This is still a serious computing problem, but generally doesn't need the very, very fastest computers in the world. And in fact, what proved to be very, very useful for computing these were these graphics processing units. So one of the first major numerical science uses of these things beyond playing first-person shooters was computing these things in Lattice QCD, and it's grown out of all proportion now. And in fact, many of the big, fast supercomputers actually use these as their computational workhorses now. But you still need pretty serious computing to do this. And then you save those to disk as well. And then you do this contraction term, this multiplying these matrices together to compute whatever correlation functions you're interested in. This is less serious computing in the sense that you're not using the fastest computers in the world, but you need what's called capacity computing. You need many, many boxes, many, many computers that you can just serially, it's usually called embarrassingly parallel, right? You just give each box a job to do, and they don't need to communicate with each other. They just each work on that. There are still computational challenges there, because typically we end up computing a lot of correlation functions using the same M inverses. So there, the job is really bookkeeping and memory management. You want to make sure that the quantities that you load into memory, you load once and use efficiently before depositing. You don't want to load them, chuck them away a bit later, load it again, because every time you have to load the things up, that's the slowest bit. So there's a lot of bookkeeping and memory management. Then you get your correlation functions, and then magic happens, which we'll talk about in the next lecture, and maybe physics comes out. Okay. So I've run slightly over. I do want to, at the start of the next lecture, I'll come to this point, which is that I promised you that this method was approximate, but systematically improvable. And I've completely fudged on that. So I'll start with this, start of the next one. Thanks.
Can you comment on how CUDA cores would be useful for computing the M inverses? I assume that's what's going on here with the GPUs.
CUDA is the name of the programming language, right? So yeah, so I wasn't personally involved in this development, but I watched it from the outside. And this was all done in the early days. Well, it continues now. There are people who work for example, NVIDIA, who got their training in Lattice QCD. So CUDA with a C, right, is the NVIDIA brand programming language for GPUs. So that was a very, very useful tool to make use of these things in the early days. Extremely confusingly, within Lattice QCD, there is a variant of CUDA called CUDA, spelt with a Q, quantum, which has lattice field theory operations built into it. But yeah, this is using GPUs for this stuff, and for this stuff is very, very, very heavily used now. GPUs are really, really good for matrix inverses and matrix determinants. They're fantastic for that, because it's one trick, right? The difference between roughly speaking, the difference between a CPU and a GPU is a CPU can do anything unexpected, right? The user can ask at any time for it to do something that it wasn't prepared to do. It's fantastic for that. GPUs are the other end of the scale. GPUs do one thing, And don't ask it to do anything unusual. Just ask it to do the same thing over and over and over and over again. Well, that's what a matrix inverse is.
Thanks.
So it says here, or you've claimed that you only need to generate hundreds of gauge field configurations, whereas for most Monte Carlo applications, you'd have to create thousands, hundreds of thousands. So what is the process? Why is that number so low?
Okay, so that's a very good question. It's not obvious from anything I've said. First of all, I will emphasize that you have to make sure you're comparing like to like. When you're thinking about Monte Carlo processes, are you thinking about importance sampled Monte Carlo or just random pulling Monte Carlo?
Just random.
Yeah, so importance sampling does a huge amount for you, right? If you are sampling the most important configurations, it's really spooky, more often, then you can guess you're going to need to have fewer. But ultimately, this number is not theoretical, right? It's from experience. So we have done this many, many times, and you saw this this idea that it's self-diagnosing because you compute the variance. So of course, people look at this and check that they're reaching a required level of uncertainty. What's more, also, if you know a bit about Monte Carlo and you know about Markov chain, where you move from one configuration to another by making small changes, it's important to realize that these gauge field configurations are not neighboring configurations in the Markov chain. You do multiple steps to get you away from a field that looked similar to the one you just did, and you throw all of those out. And that allows you to beat down what is called autocorrelations, where basically, in physics terms, the configurations look too similar, right? So they're not really independent of each other.
Thank you.
Okay.
Yeah, this might be not a good question, but so you mentioned these like pseudo Feynman diagrams. Can you like generalize that to like so say, I mean, a lot of the or storage capacity comes from these M matrices. So could you like create like a generalized Feynman diagram for a specific reaction, and then that'll give you sort of like an approximate idea of this like scaling?
Well, you actually compute this. You compute this diagram represents this.
Right.
You
I mean,
compute
like,
it and you do it on many, many, many configurations, and that is an approximate estimate of the correlation function.
right. Sorry, I guess I said this wrong. So it's like kind of like in perturbation theory. So like if you get multiple vertices, that gives you like a sort of like a scaling parameter of how important those are. I'm saying this wrong.
So you should view this carefully. This is not that you might think this looks like a tree-level Feynman diagram.
Yeah.
It is not, because this is computed on the background of the gauge configuration. And remember, the gauge configuration has all the gluons doing everything non-perturbative gluons like to do, and it has all the quark-antiquark bubbles doing all the things that quark-antiquark bubbles like to do. So this is really representing everything that can happen. So there's no sense in which this is an approximation. It is exactly the thing. Well, it's an approximation in that you are computing this on a finite number of configurations and on this discretized thing. Yeah, I'm not sure that answered your question, but I didn't quite understand.
Yeah, sorry. I mean, I'm just trying to think of a way to not calculate so many M matrices. Like if there's a way to.
Oh, there's only one.
Well, I mean, like if you get larger, I mean, if you get more.
Okay. So we haven't come into that. What if the diagram is more complicated and
Yeah,
has
that's
got
what I
more
mean.
lines on it? It's the same M multiple times.
Oh.
So in fact, what I'm showing you here is in fact not the way that people who do this for a living when they're computing complicated diagrams do it. There is a cleverer way to do it than this, but I just don't have time
I
to,
see,
to
okay.
describe it.
Because I thought they were independent of each other, so.
And then basically you compute one set of M's, if you like, and you use them over and over and over again for arbitrarily complicated
Okay,
diagrams.
nice. Yeah, that's cool.
Can you talk about the motivations that gave origin to Lattice QCD and how has it grown since then?
I mean, historically, I'm the wrong person to ask. There was a guy called Ken Wilson who dreamt it up quite a long time ago. I guess it must have been in the 80s, I would assume. And initially, it wasn't that useful because the computing power wasn't there to do anything reasonable. So in the early days, I guess for like a decade or so, people were doing calculations on tiny lattices, like 4 cubed by 10 or something. So it was really just testing things out and seeing if you could make it work in a very, very approximate way. Over the past, well, I've been doing this for 20 years now, and it's absolutely exploded in the things you can do. And in fact, the whole next lecture is going to be showing you the things that you can do now with this tool. The motivation, in a sense, well, the motivation is the one I gave, which is essentially there's no other option. If you want first principles results from QCD, you do this or you do nothing. There's no other option, right? That's it. So that's a pretty good motivation, right? Lack of any other option.
It's on your last slide, you said you can select a discretization. How do you go about selecting one?
Yeah, so actually this is slightly complicated. I don't want to get into too much of the details here, but it comes down to what I'll talk about at the start of the next slide, which is the approximation, the big approximation you've made is you put this on a grid, right? And you've introduced a separation between neighboring sites and a length scale that does not exist in real physics, right? And what that means is any quantity you calculate surely depends upon what value of A you have chosen. And you only get the right answer in the limit A goes to 0. The main thing about selecting a discretization is to try to find one that approaches A goes to 0 as fast as possible. So calculations at a finite value of A are already very close to the A goes to 0. And the analogy there is finite differences for derivatives, right? You know that you can do simple nearest neighbor, but that has corrections at the next order in A. But you can do fancier things where you have weighted nearest neighbor and next to nearest neighbor, where you cancel out the corrections at order A and get something at order A squared. You can do something similar here. It's rather difficult because this is an interacting quantum field theory, but you can do that. And that's really what selector discretization is about. The other aspect here is you can choose discretizations that have, when you put the system on a grid, you break symmetries, right? You don't have rotational symmetry anymore. And also you don't have chiral symmetry anymore. There are discretizations you can choose which sort of restore some of those symmetries. And if in your calculation it's important to have those symmetries, like a residuum of chiral symmetry, then you might choose a discretization that reflects that symmetry. But for other calculations, that doesn't matter, so you don't bother.
I don't want to put you in the fire or anything, but how much do you trust the results from Lattice? Like if you get if you get a result, would you say you're discovering new physics, or would you wait for experiments theory?
So maybe wait till the next lecture where I'll actually show you what you can do. Because right now I haven't shown you what anything you can compute is. So
Sure.
how much do I trust the value of the quark propagator averaged over gauge fields? 100%. I completely trust that will produce an approximation to 0 that I believe.
Fair.
Right. So wait till I show you something, and then in particular, I'm going to address the systematics, which is essentially the answer to your question as to whether you should trust.